Awesome. That was on point for doing all the housekeeping. So data version control. This is a very simplified view of the machine learning process. So usually when you do machine learning, you build some kind of model. And how do you go about that? You have two ingredients towards that model. One is the code. So you specify the algorithm, the architecture, your training loop within your code. And the other thing that you have is the data. So you collect some data that is relevant to your problem. In the beginning, you don't know how relevant it may be or may not be. And then as the project goes on, there's a lot of things that change. So you might do experiments, figure out that certain architectures perform better than others. You just try out different kinds of architectures. You might find a bug in your code that you want to fix. New features are required by changing requirements from management or of the project. And you're also going and you might collect new data. People are using your deployed model. You might want to use that to retrain your model periodically. Or you find out that some data or some parts of the data that you had are faulty, wrong, or just not relevant because you had distribution drift or don't need that. So we see that there's a lot of dynamics happening within the code as well as the data, which yields different versions of the model, different performances of the model. And we do treat code as a first-class citizen already. So because these data and code are the fundamental assets that produce the output, the model that we have, we do version our code using Git to enable reproducibility and work with our colleagues. But we don't really do it for data yet. At least some of us don't. And when you work on a project, you might find yourself starting and ending up with something like this. So we see that doing or versioning your data or having the need to version your data is something that just naturally comes up within a project. And if you want to move fast, you do solo experimentation. This might even be enough and fine because you do know what is V3 experiment 2. You have some kind of mental association to that. But you can also easily see that when you have bigger teams, when you want to work on a project that is bigger than yourself, so people can get on and off-boarded to the project, that this really doesn't scale. Because what the hell is between V3, experiment 3, what was fixed in version 2, and so on. And that is where data version control comes in. And this is the only lengthy text I'm going to read today. But data version control is the process of systematically tracking different versions of data sets to ensure traceability, auditability, and reproducibility. And it's also to enable members on one hand side to experiment in isolation, but also to enable to work jointly on projects. So I've highlighted the important things here. First is systematic tracking. So we have some kind of systematic way of dealing with our data. What we want to achieve with a systematic way is traceability, auditability, and reproducibility. I'm going to go this in more detail in a minute, but traceability, we want to see what are the changes that happen to the data set. Auditability, we want to understand why have these changes been made. Do we still confirm or are behind that reason why we did these changes, or do we might want to roll them back, in which case we have reproducibility, so we want to get to a previous state or to a different state of the data set. And then the experimentation and isolation and collaboration. So when I do changes to the data because I want to try something out, I'm doing an experiment, I don't want this to break or affect the code that my colleagues wrote. But on the other hand, if I have a great idea and I did some changes to the data, created a new feature, I also want to share that in an easy way with my colleagues so that they don't have to redo the work of doing that. And there are several tools you can use to go about data version control. You see some of them on the right. So DVC, DOLT, LakeFS, Git-LFS, or Delta Lake. And yeah, LakeFS is the one that we going to present today because it's the one that we like most. But in case you want to do your own research or think you have differing requirements, there's a couple of logos for your own convenience to look up after. What do we do with these data versioning tools? So I've hinted at this in the definition before, but traceability, so the actions, the changes that we do to the data is something that we want to have recorded, and we want to reference these different versions, or want to be able to reference these different versions, either with a timestamp or an identifier, but just somehow to have some way to point at the specific version. And that ties in with the next point, reproducibility, so being able to retrieve that previous version of the data set, and being able to add additional metadata, so commit messages, something that explains why did you do the changes that you did, or some other parameters that you do want to log. And then the last thing, the collaboration. If you're familiar with Git, it's just being able to branch off the state of the repository to work with it and being able to merge it back if you want everybody to be able to access your changes. And that's enough with the theory of talking about data version control and what it is. And now we jump in talking about LakeFS. So LakeFS is an open source project enabling you to do data version control and roll back with a data lake. It's conceptually really, I mean, obviously software-wise it's working a bit different because data is different to code, at least also the amount that we have and so on. But it brings really familiar interface to data. So you have a Git-like interface with where you have your object storages underneath. So your data sits either on on-prem servers or you can have it in the cloud. And you have then the representation where you can tag, revert, commit. You can revert those commits and you can merge and fork branches. The commit snapshots are pointed or like capture the repository at the specific point in time, and different to other tools like Delta Lake, LakeFS really creates, it does it in a smart way, so it does not just plainly copy the repository, but it has access to the state of the repository at the time of every commit, and does not need to run through all the diffs to create the state of the repository. So this is what a commit snapshot is. I've talked about the cloud support, so all the common clouds are involved, so AWS, Azure, GCP, or your own backends. And there are third-party integrations, so Spark or Data Lake or Iceberg, if that's something you're interested in. And then, briefly showing you off how LakeFS looks like. So you see that it's really like the UI really looks similar to what you are familiar with probably from using GitHub. So you have a central repository where you can have either directly files in there, or you can have folders and a README that is down here. So this is also I've changed the name to PyData Heilbronn, but if you use their LakeFS and just click create the quick start example, this is exactly what you see. And you can then also see in the menu that we can look for uncommitted changes. We can see the commit history. There's not much in there yet because the repository was created and we have the sample data. We don't have any uncommitted changes. We don't have any additional branches besides the default main branch. But this really gives you an intuition on how LakeFS looks like and how you would interact with it. And there's really conceptually nothing new here. If you're familiar with Git, this will feel really like home for you. How to do versioning with LakeFS. So now that we're familiar with Git, so we also recommend working with branches so that if you are interested in a specific state of the repository, you branch off that. And if you have, for example, a continuous on your main branch, or you're collecting data continuously and you're working with that data, and you would always reference to the main branch that gives updates, the view that the data that you would experiment with would also be updated, and you have an uncontrolled variable if you, for example, think about accuracies or so on. So if you then branch off, the new data is only added to the main branch. Your old branch stays the same, consistent, and you can eliminate this confounding or this variable, this other uncontrolled factor in your experiment. You commit your versions whenever you made a change that you think that is atomic, that you think you might want to roll back at a later point or just reference to. You can create a commit, and you can use these, and we will do that in practice in a moment, use these commits to reference to do reproducibility. And with that, we now go to the practical part of using LakeFS-Spec, which is a library that we at appliedAI developed and open sourced to interface with LakeFS from your Python projects. And that is basically the aim of LakeFS-Spec is now to make the LakeFS versioned data available with a file system interface. And you can basically work with with it like you would normally do. So we have here in the LakeFS main repository, if we look at the lakes file that I've briefly covered on, we see that it's just a collection, a big collection of lakes. And if we go now in the Jupyter notebook that I have and look in there, we can see that we indeed got the same file here. As you also noticed, we haven't imported LakeFS-Spec yet, but we have installed it in the system. And that is to just read and from the files. That is enough because we have added the LakeFS file system to the underlying file system. So when you use this string and pass it to any library that uses FSSpec as a file system under the hood, and these are Pandas, probably the most common one, but also DuckDB and others. So everything that is based on FSSpec, if you install LakeFS-Spec, will, when you start your file path with this identifier, know how to parse whatever is coming afterwards. And whatever is coming afterwards, in this case, is just me specifying first the repository that I'm working in. So if we look in LakeFS so this is the repository I'm working in. And then I specify the branch that we're working on, and I specify the file. And without anything, so you get just reading from it, just by having a LakeFS-Spec installed, gives you the ability to read from your versioned data repository. We can write files the same way. So let's say we want, for whatever reason, just the German lakes out of that file. So we briefly create that and now want to write that to the file system. Now we need to import something, and we get the LakeFS file system object from the LakeFS-Spec package. And then we use what we call we use a context manager, the transaction context manager, to really conduct our versioning operations. What did we do here? So we have this transaction context where we again specify the repository that we want to operate on, and we specify the branch that we want to operate on, and get that in this handy transaction object. And then we can just write to with the same logic that we just talked about, write to the repository of the branch and give it a file name. And then we can also do a commit and get a commit message. We could even write without using a transaction, but in this case we want to do a transaction because we also want to do the commit of so we don't want to have uncommitted changes dangling around. And now if we go here and look on the commits, we do see that the German lakes file was indeed added here. What we also see, what is very important here, is this other new commit message, and this is because our transaction that we have here creates an ephemeral branch, so a branch that does not or that is deleted afterwards, but we do this in order to safeguard the operations that we do. So if somewhere in here an error would occur, you don't really want to have an unfinished state on your main repository and polluting, or on whatever branch others might also depend on. So the transaction creates a new branch, conducts all the specified, or everything that you coded up here, conducts that on the branch, and only then, if the context manager exits without an error, the branch is merged back. So this helps you to, if anything goes south within the transaction, to not have that polluting the state on your branch that you're working on. Especially important if you were to use this logic or LakeFS-Spec in kind of automated jobs where you definitely don't want to have some weird states in between. We can, for now, we have worked with data frames, but we can also access arbitrary files. So in my repository locally, I just have an experiment.json file with some dummy data in. And again, we start and conduct with nothing really new. So we start with the transaction, where we again specify the repository and the branch. Then we open the remote file called experiment.json. We read in here in this line the local file. We can dump onto the remote file on our data repository and add a commit in the end. And when we now look into what happens, so I'm refreshing here, and we again see that our experiment.json file has been added, and we also see the commit from the safeguarding branch that was created. We can also do more complex versioning operations. So for now, we only did writing and committing. But let's say we are doing a more complex experiment, which involves us doing a train test split. And then we want to have a specified branch that we can work on for longer time. So for that, we can again work with with our transaction context manager. And in this case, we specify the PyData repository. We give in the base branch, but we can also specify the branch name that is so that it's not an automatically created ID that we have seen here. So these numbers were auto-generated, but we can just fix the name and want the branch to be called demo experiment. And then we use the second argument, which is on one side delete never. So in this case, the branch is persisted and is not deleted when we exit the transaction context manager. And we also set auto merge to false, because as of now, we always deleted these transient branches and merged them before we deleted them, merged them back into the main branch. So we don't want to merge in this case, and we don't want to delete. But then, as we did before, writing the file and committing what we have. And then, indeed, if we look here, we do have the demo experiment branch on there, which also now contains our train and test files, which are not on our main branch. So with this, we've created more complex versioning operations. And other things that we can do is, for example, using tags. So we've looked in here, and if we look at the commits, we see the commit char, so unique identifiers here. But if you want to have a specific state of your repository that you want to refer to more often, it's really inconvenient to just remember a random string of numbers. That's where tags come in. So here we just put the PyData demo tag onto the commit that we've gotten down here. So when in this case, we did do the commit, and we took the commit or wrote the output of the commit into a variable, and we now here have the commit and can access its ID object, ID property, and we now create the reference of a tag and just give it the name PyData demo. And now whenever I use PyData demo, it actually points to that very commit. So I don't need to remember or use that long string of names, but I can just specify the repository, PyData demo as the state of the data that it's in, and then use the files, the file name, and then I get the test.csv file at that point in time. But if we want to do automated versioning, so we use something like MLflow to track our experiments, and we want to have reproducibility and know exactly what is the state of the data, which data went into that, we would work with the commit ID that is in the commit object, so log that. And we see now if we execute this and just take the commit object, we see that it's indeed also getting the lakes.parquet file from the same state of the repository at that point in time. And with that, I'm coming to the end of my talk. What did we learn today? So we've talked about data version control. We've talked about LakeFS and LakeFS-Spec, and that enables you to do easy read and write operations just by using the URIs instead of your natural or usual file paths. With LakeFS, you can do Git-style versioning for your data, and LakeFS-Spec provides you transaction as a safeguarded way to programmatically conduct these versioning operations. And there are also two niceties that I haven't really talked about, but we have within LakeFS-Spec automated discovery of authentication credentials. So if you have a config file around, it just uses that, but you can also pass the authorization when you instantiate the file system. And we also have enabled caching. So if you have larger files and want to up and download them, we check if they have changed to the state that is on your local machine, and only send data over the network if that is really necessary. And If you have any questions, the time is now. This is a link to the GitHub repo, and it's open sourced and on PyPI already. So if you install LakeFS and do pip install LakeFS-Spec, you're ready to go to do whatever you want to do with it. Thank you.
Yeah, thanks, Max, for the talk. Questions? Who's first? Who works with data versioning? Simon has a question. I saw your hand. It moved. Yeah, Simon.
I didn't want to move for the second part of the question.
Oh.
First of all, thank you. Very interesting talk. Can I also use LakeFS to version entire image folders, for example? I'm thinking back of my computer vision projects.
Yes, you can use LakeFS. So this is not only files in the repository, but you can also have subdirectories. So there's any kind of file in there. So for textual data, they have some kind of nice preview functions that are not available for other data types. But in principle, this is just, as long as you can store it as data, you can version it with LakeFS.
And then maybe a follow-up question. Is there an upper limit in terms of the amount of data that LakeFS can efficiently handle? Do I run into some issues if I just dump a terabyte or something?
I think for a terabyte, you should not run into issues. Jan might know a little more about the upper bounds of LakeFS.
So let's go to Jan, Willem, here.
Yeah, this is actually one of the reasons why we sort of like LakeFS better than the other list of tools. I think the most popular tool out there is DVC, but you notice that if you do like, I'd say hundreds of files, DVC will get painfully slow. It's known, it's just not made for that, and that's not a problem. The nice thing is that LakeFS comes out of a company, and they're really like big data experts, and they know what they're doing, and they have spent a lot of time and effort on these kinds of cases. So terabytes is really not an issue. And the nice thing is it's built every time in a scalable way. So you have the object storage in the back end that can handle up to whatever provider you have. But also the way how you can access files. You can, via pre-signed URLs, you can shortcut, you can scale it up, but having multiple gateways. So there's all sorts of things built in to not let you run into to those kind of problems.
Thanks. More questions? Yeah.
I'm just interested how this works internally. Let's say you have this 1 terabyte file and then you change only like a byte or so and have a new version. Like, is it completely copied, or does LakeFS only store the diff between the original file and the change?
So LakeFS does not work like Delta Lake, which only stores the diffs. So I think it detects the files that have been changed and copies those. So if you have one very large 1 terabyte file and flip a bit, I think that file would be now stored twice. But it does not just copy for every version the whole data repository, but just has a smart system underneath of pointing for every commit to the versions of the file that it wants to have, and it then only copies or has a new version for a file when that file also was changed.
If you go to the LakeFS website, there's quite some backend.
People won't hear you on the stream.
Sorry. If you go to the LakeFS website, there's quite some background information on how they designed it, and you can sort of see what makes sense to do and where you have to be a little bit more careful.
So, Thomas has a question.
Yeah, never having worked with data versioning, I would be curious to what extent merge conflicts and resolving those is practical on large files.
I would expect that when you have, so personally I haven't really run into problematic merge conflicts. I think if your data set has a sufficient size, doing that manually is not practical. So it would probably run down into thinking about what were the changes that were applied and which versions do you want to give precedence to. yeah, that is my gut reaction, how I would deal with that without ever having faced the issue.
No, it's a big question. Jan, do you agree?
I mean, the thing is, similar to when you're writing code, there's all sorts of different flow models on how you collaborate, on when you merge, on how you communicate, and that problem in that sense does not go away for data. You need to architect how you work. But it really depends on the use case and what you're doing. Initially, when you're experimenting a lot, you could also say it's like it doesn't make sense to merge back into one main branch. You just have multiple experiments next to each other. If you have a production system, for instance, that ingests data on a regular basis, then you say, okay, that process goes into the main branch, but experiments are branching off and never go back. Just make sure that you always have a pipeline. And the idea is that if it gets difficult to merge back into a single branch, that you actually start making hierarchies of branches. You can get quite far and quite advanced with it, but you have to really plan it and architect it if it gets bigger.
Somebody last question? No? Then thanks again for the talk, Max.
Thank you.
Here.